Hello and welcome back to another VMK in the game development series. In this VMK we're going to be modifying our scene class so that we can start using the scene graph stuff that we've been developing up till now. If you're finding my videos helpful and you'd like to support the website, please click on the PayPal icon or click on any of the Google ads found on the side. The more clicks you make, the more support that you'll be giving me. Alright. Let's go take a look at the scene.h file. As we see here, we have a bunch of public members, and then we have some private members. The first 5 functions here under the privates deal with lights. I'm going to group these together just to clean them up a little bit, like so. And we're not going to be touching the lights for now. Then we have a bunch of functions here that deal with textures, and then we have a bunch of functions that deal with fonts. What I'm going to do is I'm going to comment out all the functions that have to do with the textures. Our textures are going to be handled slightly differently than they were before, so we'll have a separate VMK on how to change these functions here. But I'm going to take them out now because I want the compiler to give me error messages if I do want to try to use these, because they're not being handled the way that we want them to be handled. Same thing with the fonts. We won't be able to use the fonts if we have the textures disabled, so I'm going to comment out the fonts as well. Now we need to interact with the scene graph, so we need to create the following functions. We have add node, delete all nodes, save geometry, and delete all geometries. And inside this VMK, I'll show you how to implement these 4 functions, and then once we do that, we'll be able to render things to the screen. Down here, under the private members, we have a container for lights, we have a container for textures, we have a container for fonts, and then we had the members down here, the objects in our scene. Well, we've converted the flat grid already, so we can delete that object. And we need to create 2 new containers down here. And the 2 new containers are going to hold node pointers and geometry pointers. We have created the node shape as well as the node transform classes, and both of these inherit from the node class. Because of this, we're able to create this std vector that will contain node pointers. And what this means is, anytime we create a node shape or a node transform, we can store it inside this std vector, and it will keep track of everything for us. Same thing goes for the geometries. Underneath object.lib here, we've created 2 different kinds of geometries. We have the box and the flat grid. Now, normally you wouldn't be able to stick either of these inside this vector because the classes don't match. But again, because we've inherited from geometry class, these 2 classes themselves are geometries. So we are allowed to put those inside this container. And when I say container, I mean this std vector is just like an array that can store items. And each item that's stored in there is going to be indexed for us. And the items that it's storing are pointers to geometries. So those are the 2 new containers we'll be adding. Now, those are the changes we'll be making to the .h file. Now let's go and open up the CPP file. Oh, actually, there's one other thing we need to change in here, and that's up here. I'm pretty sure we can delete color OpenGL. I'll comment it out for now because I'm not positive on that. We won't need flatgrid.h anymore since it doesn't exist. And instead, we're replacing it with geometry flatgrid.h. We're adding up here geometry box.h as well as the node shape and the node transform. And we're going to leave the light stuff as well as the texture stuff for now. So let's save that. Okay, now let's open up the CPP file. We'll start off with the clear all. Clear all gets called whenever we call the destructor up here. And right now what we're doing is we're clearing all the lights, the textures, and the fonts. Now because we've taken out the textures and the fonts functions, we're going to need to comment these out, as well as anything to do with MP grid or MP ground we need to delete. And what else? Well, we've added these new functions here called delete all geometries and delete all nodes. So these should be called inside here as well. Let's just change this comment here, get rid of all so we're going to delete all lights, delete all geometries, and delete all nodes. It doesn't matter in which order you perform these operations, so you can list them any way you like. And let's see here. Player action, we don't change. And update. Okay, under update, we're going to be making some heavy changes in here. But before I show you what changes we're going to make here, I want to go and implement the rest of the code first. So we'll come back to this one a little later. And then we got light stuff near the bottom here, which we're not touching in the HUD. Okay, the HUD is all right because it's all commented. So we're not going to be displaying anything to the screen. Let's go inside the initialize. Inside here, okay, here we've created a bunch of things. We have the houses, the ground, the light sources, and a bunch of textures. Well, let's just start clean and go from there. So we don't need all of this stuff. Let's just delete it all. Okay, so we have a clean initialize function. I'm leaving the eye level because the player still needs to have a reference point for where the eye is going to be located. Before I describe what we're going to put inside this initialize function, I guess I need to overview what all these new functions here, add node, delete all nodes, save geometry, and delete all geometries, what each of these functions are supposed to do and how they intend to do it. Because inside initialize, we need to initialize our scene graph, and the scene graph has to get constructed dynamically. So in other words, whenever we're going to be loading in each of these nodes, we need to construct a method to make sure that our scene graph actually gets created in the structure so that it's actually a valid scene graph and all of the nodes are nested appropriately. So how do we define a valid scene graph? Well, there's a couple rules we have to abide by. Rule number one is transformation nodes are the only kinds of nodes that are allowed in the root. Now when I say the root, let's go back into PaintShop Pro and take a look. Our root is going to be coming in from the very top, and actually it's better demonstrated here in VRealm. So the root here is called New World, but we're not going to name our root, it's just going to be called root to us. So the very first node we see has to be a transformation node. It cannot be a shape node or any other node that we create. But for now, we only have shape nodes and transformation nodes. So rule number one has to be a transformation node at the root. This transformation node down here is also at the root because you notice it's branching from the root. So it also has to be a transformation node. Just remember that you're not allowed to put anything other than transformation nodes at the root. Rule number two is a shape node has to be nested underneath a transformation node. It can't be nested underneath a shape node. So you notice this shape node here is the child of this transformation, and that's perfectly valid. But we can't have a second shape node nested underneath this shape node. We can put a second shape node underneath the same transform node, so this transform can drive two shape nodes, but we can't have a shape being a parent to another shape. That's not allowed. So those are the two main rules you have to remember. And if I think of any more, then we'll talk about them in detail. Now let's go back into PaintShop Pro. Let's say we've created a structure that's already like this. Now you may be asking, how did we go about to create this? Well, this is what I'm going to hopefully be able to explain in this little series of images here. So let's say we already have the structure formulated from previous work we've done. Now, we want to add an extra node to the scene. So let's say we wanted to add a child to N3, okay? So let me get a marker here, and let's say we wanted to place N6 right here. How would we do that? Well, we go and create N6 just as we normally do, and N6 could be a transformation node if N3 is not a shape node, because we're not allowed to nest anything underneath a shape node. I'm not sure if I mentioned that or not, but that's another rule. Nothing's allowed to be nested underneath shapes. So if we do nest N6 under N3, that means N3 must be a transformation. Okay. We need to know the location of N3. And N3 is stored inside of an array, so we can pull the pointer for this guy out. When we have the pointer for him, we'll see that there are 4 pointers associated with him. And those 4 pointers are located here. We have pin, pout, pnext, and pprevious. And according to the color coding, you can see that we've already defined pout for N3 because it's pointing to N2. Pin for N3 is pointing to nothing, so it doesn't have anything. And pprevious and pnext are also not showing up here, so they're not pointing to anything. Which means we're allowed to nest something underneath here, or we're allowed to have something next to this guy. But as we said before, let's say we want N6 to be nested underneath N3. Well, what does that mean? That means that our function that's going to do this construction needs to do the following. It will need to create a pointer, let me get this color here, for pin, and attach it so that it points in this fashion. So N3 pin value has to point to N6. And at the same time, we need to make sure that pout for N6 will point back to N3. If we are successful in associating these 2 pointers this way, then we'll have successfully nested N3 and N6, or I should reword that. We'll have successfully nested N6 underneath N3. So that's the operation that our function needs to do. Now let's say that instead of nesting N6 underneath N3, we actually wanted to put N6 beside N3. How would we do that? Well, let's say, let me just move this over here. And okay, we want to have N6 beside N3, not nested. So in other words, N6 is now nested underneath N2. How would we do that? Well, what we're going to give to our function is we will, let me get a black marker here. We'll say, I want to nest underneath N2, and what I want to nest is N6. So our algorithm has to be smart enough to say, okay, if I'm going to nest underneath N2, take a look at the pin value for N2. However, pin value for N2 is already defined, and it's defined to be pointing at N3. So the next thing our algorithm has to do is say, okay, there's already something nested underneath N2, so go to the next value at this child level. So then we're going to look at the next value for N3. And because it's not pointing to anything right now, we'll then be able to associate it. So again, we're going to go and select this pointer, which is mpnext, and make it point to N6. Then we need to take N6's previous value, which I've labeled here brown, and point it back to N3. And by associating these 2 pointers, we've now appropriately attached N6 to be nested underneath N2. That's the way that our algorithm is going to work. So remember, we're going to give it a node that we want to work with, so for instance N6, and we're going to give it an ID number for a node that already exists. And we're going to tell it we want to nest it underneath this node. Now how do we nest underneath the root? Because each of these are going to be stored inside of an array, so we can easily pull the node information out of the array using just the array. Well, if we want to nest things under the root, we don't have a location for the root. So we're going to create a very special ID number, and we're going to call it ID 0, and that's going to say we're nesting underneath the root. So now let's say we want to create a new node, call it N7, and we want it to be underneath the root. So what's going to happen is we're going to look at the root and see if there's anything inside the root. And of course, there's going to be something inside because we have N1 inside the root. Well, then we look at the next value of whatever's inside the root. And the next value would be the next value for N1. And right now, we don't have any green arrows pointing down from N1, which means that there isn't anything there. So we can go ahead and take our MP next value and connect it up with N3, like so. My drawing is getting pretty terrible because I'm drawing with a mouse here. And then our previous value for N7 will need to point back to N1. And by doing that, we've now appropriately attached N7 to be nested at the root, which is here, and it's also attached to the next value of N1. So I hope that makes sense. Take a look through the way that things are getting connected, and hopefully you'll understand how these pointers are getting associated. So now we can go back to the question of how do we start this tree, because initially there isn't going to be anything at the root. So let's go and take all of this out. Actually, let me just create a very brand new file here. Okay, and pick black here. So initially, our ID number is going to be 0 to pointing at the root. The root is always associated with 0. And initially, this is not going to be pointing to anything. So our algorithm has to, again, accept two things. Accept a node and accept an ID number. And the ID number is going to be 0, and the node is going to be the first thing that we want to attach to the root. So when we call our function, we're going to pass in 0 and pass in our node. And because there isn't anything associated with 0 right now, then immediately we place our first node down here, N1, and the pointers do not get assigned because there is nothing else that we need to do. Now when we create N2, let's say we created N2, actually, let me put N2 right here. I want to say, take N2 and also put it on the root. Well, what's going to happen in the algorithm is I'm going to pass in 0 to represent I'm attaching it to the root, and the algorithm's going to go into the 0 and see it's already pointing at N1. Well, because it's pointing at N1, it then looks at the next value for N1. And since there isn't anything assigned to the next value, it automatically makes this connection for N1 and also makes this connection for N2. So the next value for N1 will point to N2, and the previous value for N2 will point back to N1. Now on the third node, let's say I want to attach N3 to be nested underneath wherever N1 was located. Well, I'll give this location here for N1, and that will happen to be the number 1. And I know it's number 1 because the first node I place into an array is going to be indexed 1, the second one is going to be indexed 2, and so on. So I'll pass in node 3 and number 1 and say connect them together. So the algorithm's going to go in here into N1 and say take a look at the in value. Well, there isn't anything attached to the in value for N1, so it's going to immediately attach it to N3. And then N3's previous value is going to get attached to N1. So that's the way that the algorithm's going to work. Now let's go take a look at the code to implement this. First thing we need to do is create our node and then call our special function to make this association with all these pointers. Okay, let's see what we have here. I created an unsigned integer, called it UI node ID, and this is going to hold the valid ID number that our add node function is going to return. So once it puts a node into the scene graph, it's going to return the ID number for that location. So that if we want to nest anything from then on, we need to just use that node ID number. Then we create a pointer to a node transform, and we start off with a node transform because, as I said, the only thing that's allowed inside the root is a transform node. So it has to be the first thing you create. So we call the new operator on node transform, and if this succeeds, we go down here into the else. Otherwise, we generate an error message and display it to the screen. So if we can allocate the memory to create this node transform, then we can assign whatever values we want to the transform, but I'm not doing that. I'm just using the default values. And then I'm adding this node to the scene graph. So this function here is going to make all the connections inside the scene graph. I pass in the pointer to this node transform, which we created up here, and we're saying the nested value is going to be 0. So in other words, we're nesting it underneath the root. Let's take a look at this add node function. These are one of the new functions that we need to write here. Okay, we'll put this add node function, let's just put it right above initialize here. And let's take a look at what we're doing. We're getting the pointer to a node, and we're getting the unsigned integer for the nested ID. If the pointer that we pass in here is null or invalid, then we just generate an error message and we return 0. Anytime that this function returns 0 means that something wrong happened internally. We then take a look to see whether this nested value is greater than the total number of nodes we have saved inside a container. And remember again, inside the .h file here, we have this variable here which will contain all of the nodes that we're putting inside of our scene graph. So here we're just checking to make sure that the ID value is valid if we are nesting it underneath something. If it's not valid, we immediately delete whatever the pointer was passed into us here, and we return 0. We need to do this delete here because, if you remember, outside of our add node function, we call the new operator, so we allocate new memory, but we won't be deleting it anywhere down here. So the only way to delete it has to happen inside add node or inside delete all nodes. But delete all nodes wouldn't know about this new guy if there's an error message generated in here. So that's why we need to delete it internally. Okay, so if the nested ID, or sorry, if the nested ID here is invalid, we delete it and we return 0. Otherwise, we continue on through. Then we have an if statement. We check to see if we're nesting it in the root. If we are under the root, we handle things a little bit differently than otherwise. And otherwise, we need to basically find the node that we want to nest under. So first, let's take a look at what we do when we nest under the root. First thing we check for is to see whether this node that we're passing in here is a transform node. And remember, one of the rules is only transform nodes are allowed inside the root. So if it's not a transform node, we generate an error message, we'll delete this node, and we return 0. If it is a transform node, we then check to see that if the size of the container holding all the nodes is not equal to 0. In other words, is there already something stored inside of our container? If it's not equal to 0, that means there is something stored. If it is equal to 0, that means nothing's stored there. So we don't have to handle anything differently. And instead, we'll just go straight down to here and take the node value that was passed into us and push it right into our container. And then we return the size of the container, which will then act as the ID number for this add node that gets returned. If there's already something stored inside the container, then we need to do this check for the pointers and then assign the pointers appropriately. So what we do is we create a temporary pointer to a node and we assign it to the very first value stored inside of a container. And then we go inside a while loop looking at the next value starting from the very first guy inside the scene graph. And we continue going through this loop, going to the next guy and the next guy and the next guy until we get to one that has no next value. So if you remember back in here, we started at N1 and we're going to go to N2 for instance, and then as soon as we have no next value here, then we stop and we have the pointer that points to n2. Having that, we can then assign the p node's previous value to be equal to this guy that we just found. So in other words, where's my drawing here? So in other words, we're going to take, this is the node we're inserting, we'll call it n4. We're going to take the previous value for this guy and point him to n2, and then we're going to take n2's next value and point him to n4. And that's what this here does. So we set the previous value to whatever we found, and then whatever we found's next value is going to point to us, which is whatever we passed into this function up here. So that creates those connections for us. And then we exit out of that if statement and we push the node that was passed into this function onto the container. And again, we return just the ID number. So that's what happens if we want to nest things into the root. If it's not under the root we want to nest things into, then we go into here. So the first thing we need to do is find the node that we want to nest under. So we get the nested value -1 because the containers are index 0. So we get this temporary pointer to a node here. We then check to see if this temporary pointer is a transform. If it's not a transform, then it's a problem for us because we're not allowed to nest anything under a shape node, for instance. So that's why we generate an error message here, we delete the node, and then we return 0. If it is a transform, we'll continue on through. And we check, is there something inside of this current location? So again, let's say we're here at n3. We check to see if there's anything pointing inward. If there isn't, then we set the temporary values in equal to us, and then we take our out value and set it up to whatever temp is pointing to. So that creates the double connection here. So that'll create, let's say we're adding n5 here. So we're going to make this connection, and then we'll make this connection back. So that's what this right here does. And then after that, we exit out here, and again, we push this current node onto the container and then return the ID number. If there is something already inside of this current value that we want to nest under, then we need to take the in value and go through all the next values inside this scene graph. And we continue doing this until we find one that's empty. So in other words, if we go back here, it's similar to the operation we did here with n0. Let's say we want to nest underneath n3. Well, first thing we're going to do is check to see if there's something inside him. Well, we see n5 is already inside him, so we can't attach him to the in value of n3. Instead, we're going to take this guy, the pointer to this guy, and check his next value. If his next value points to something else, if it pointed to n6 for instance, then we need to move over to n6 and check his next value. And we continue doing this until we find a node that doesn't point to anything. As soon as we find that node, we then place our node here, attach the next to us, and then we take us and attach the previous pointer to whatever we found here that's valid. So that's what this here does. We loop through all the next values up to the end where we find one that doesn't point to anything, and then we set that node's we set our previous value to that temp value, and then we set that temp value's next value to us. And then again, we push ourselves onto the container stack and we return the node ID. So it's a little bit complex, it's a lot of pointer math, but I hope I've been able to explain how this scene graph is constructed. Okay, let's go back down here. Now, what is it that we want to actually initialize and create and render on the screen? Well, let's go and try to create the following. Let's create a world that has the root node, and inside the root node we're going to have a transformation node, and inside this transformation node we're going to place a shape node. And the shape node we're going to place is a geometry toolbox. And then we're going to create another transformation node down here, which is also going to have a shape node, and then this shape node is going to have a geometry of a flat grid. So when we're done, we should have 2 transformation nodes, 2 shape nodes, two different geometries, and on the screen we should be able to see two gray things, a gray box and a gray plane underneath us. So let's go and construct this inside C++. We have our first transformation node done here, and as you see, we've added it to the scene graph, and it returns the node ID pointer for the location of this transform node. Well, now we can go and create a shape node. Now, before we create a node shape, we need to first create the geometry, and I can show you this because underneath node shape, the way we created the constructor is we need to pass in a pointer to some geometry. So we can't pass in null here or else our shape node won't work. So we need to create a geometry class first. So let's do that. We'll create the box first, so we're going to create a geometry box, and this is going to be a pointer to this geometry box, and we call the new operator, passing in some values for the width, the height, and the depth, or I guess I called it something else, the width, the depth, and the height. So we pass in the width, the depth, and the height inside this constructor for the geometry box. If this succeeds, we then continue on down here, otherwise we generate an error message. So here we call save geometry, and we pass in the pointer to the geometry that we created up here. Let's take a look at what save geometry does. Let's place this function, let's just put it underneath add node here. So we're passing in a pointer to some geometry, and we check to see if this pointer is valid. If it's null, then we return an error. Otherwise, we just take that geometry and we push it onto the container that will contain all of our geometry pointers. And then we return the ID number for that geometry here. The returning of the ID number is kind of optional. I don't think I'll be using it, but I'm doing it just to stay consistent in case I need it later on. So here we've saved the geometry now. Now that we have it stored, we can then go ahead and create the shape node. And to do that, we create a pointer to a node shape, and we call the new operator. And here we are passing in the pointer to the geometry we just finished creating. So here we should have now a new shape node. And if this is invalid, then we return an error message. Otherwise, we go and call add node. And now notice what we're passing in here. We're passing in the shape node as well as the unsigned integer node ID, which was returned up here. So this is going to say, take this shape node and nest it underneath the transform that we created up here. So that's going to create the appropriate structure inside the scene graph. So we've done the first half of this scene construction here. Now we need to go and create another transform nested at the root, and then another shape node nested underneath that transform. So the process should, you should now start to become a little bit more familiar on how this scene is actually being created. Let's go ahead and create another transform. So again, we can actually, we don't need to initialize this. We can reuse the name from up above. So we're calling a new node transform. And again, we're just going to call add node, pass in that node transform, and we're nesting it underneath the root. And again, we're getting a new node ID number passed out of here. Now, technically, you should be checking these return values to make sure that they're not 0, because if something does go wrong inside here, the return value is going to be 0, and then that could mess things up if you try to automatically dump in some shape node underneath this node if it's happened to be 0, so you'll get even more error messages. But for now, I'm not doing any more extra error checkings here, so just remember that. Okay, so we have our second transform initialized here. Now we need to go and create a second geometry. First thing we're going to do is create a geometry flat grid pointer. So I'll call this p ground, and we're going to call the new operator on this p ground, and say we're going to create this ground to be 15 units wide and 15 units deep, that has been divided up into 20 divisions in the x direction and 30 divisions in the z direction. If this is valid, we then go and save the geometry. And after we have it saved, we can then go and call a new node shape. Actually, I can just do this. So we call node shape, we pass in pground this time. And if everything's fine, we just add the node and nest it underneath unsigned integer node ID, which happens to be the second transform node that we created here. And that's it. So that's all we need to do in the initialization phase. Now for cleanup, in here we're calling delete all geometries and delete all nodes. So we need to write these functions, delete all geometries and delete all nodes, because we haven't defined them yet. So first we'll do delete all geometries, and I'll put that right underneath save geometry here. So with delete all geometry, what we do is we go inside of a for loop and we create an iterator that points to the beginning of the container, and we're going to continue iterating until we're not at the end. So we'll continue going through, and each time we'll just iterate once through this iterator. And we're going to call the delete of that iterator value. So in other words, what we're doing is we're calling delete geometry, where geometry is the pointer to the geometry we stored earlier. And then after we delete all of them, I just call a clear function just to make sure that this container doesn't have any values in it. And that's all that's going to happen for the other delete all, what did I call it? Delete all nodes. And again, I'll put that right underneath add node, just to kind of group them together. So here we add nodes, and underneath here we're going to delete all nodes. And again, we have an iterator that points to the beginning of our nodes, the container that holds all our nodes. We continue going through until we get to the end, iterating once at a time. Then we call delete for this specific node. Excuse me. And then after we've deleted them all, we just call the clear. And I think that's it. So let's save this and see if we can build this. All right, we got a bunch of error messages. pground not defined. Right, we deleted our old method of rendering the ground, so we now need to go through our code and delete all instances where it needed to be used. Select texture. All right. Actually, I've changed my mind here. I've commented out these functions because I didn't want to use them, but looks like I think it's going to be more trouble commenting them out than not. So actually, let's put them back in for now, just to get rid of some of these error messages. Load texture is not a member of scene. Oh, I missed one here. Okay, that minimized the number of errors. Now we just have to go through and remove all of the stuff we're not going to be using. Oh, as a matter of fact, I forgot to update the update function. So let's do that next after we finish building the project. Let's first get rid of all of our error messages. Okay, we got a linking error. Unresolved symbol, geometry, flat grid, update. Oh, let's take a look at geometry flat grid here. We have a function called update, but we forgot to actually write it up in C++. Let's take a look at geometry box here for update. We wrote it up for this one, so let's just copy this guy and paste him inside flatgrid.cpp. I'll just put him at the very bottom. Like so. Again, I'm leaving the updates blank because we're going to implement them a little later. Okay. So that looks okay. Now all we need to do is inside of the update function be able to render everything inside the scene graph. And remember, the old way of doing it, we needed to go through every single object and call its render function. And then that render function would determine whether it's OpenGL or DirectX, and then depending on which one it was, it would then render the scene appropriately. Well, now we have a scene graph which contains all of our objects, so we don't have direct access to those objects. However, we can still render them, and this is the way we do it. Inside the scene, we're going to call the switch statement to decide which renderer we're using. We're going to be using OpenGL, so we're always going to go inside of this case. And inside here, we're taking the very first item inside of the scene graph at the root and calling its render OpenGL. I'm passing in true into the parameter for this render call, but this true value isn't going to be used anywhere just yet. We're going to come back to this a little later. Now, because render OpenGL is a recursive call, this one render call is going to make everything inside the scene render itself. So we don't have to call anything else. We don't have to go through each of these nodes and render them ourselves. The scene graph will take care of that for us. So that's it. Pretty simple to render everything. Let's compile this and run it and see what happens. And we don't see anything on the screen. Okay. What could have gone wrong? Okay, after some searching for the error in their code, the solution is actually quite simple. We enable lights, we render, and then we disable lights. So in our scene, we need to have some lights because we've told OpenGL that we're going to be rendering with lights. And the way that our objects, or I guess I should say our geometries are constructed, they all have normals. So as soon as we define a normal, we need to have a light source, or else nothing will be rendered on the screen because everything is basically not visible. So we can fix this quite easily by going inside the initialize and adding a light source. So here right at the very top, I just create a point light source, same way we've done it before in the past. Set the position to be 5 units up above the 0, 0 point so that it's illuminating straight down onto the scene. And then we have the exact same stuff we had before here with our 2 transforms and their 2 shape nodes with the geometries down below. Now let's build this and give this a run. And now you'll notice, there we go, we have something rendered on the screen. However, if you remember, I rendered a box and a plane. Well, if I look around in all different directions, I can see the plane, but where's the box? Well, the solution is quite simple once again, if you think of what we've done. We've taken the box and the plane and both rendered them right at the center of the scene. And right now, we are standing at the center of the scene. So we're actually standing inside of the box. We can't see the box because the back faces of the box are getting culled. We're looking at the box from the inside out. And because the way we've defined each of the faces of the box in terms of the counterclockwise order, we can't see them from the inside. We can only see the box from the outside. If I happen to jump, well, I guess you can't really see it very well, but if I just move away, you'll notice that I can now see the box. The box basically was standing right on top of us. The other thing is, you'll notice that the ground is gray, but the box appears black. Why is that? Remember I told you that all of our objects will look gray. Well, our box doesn't look gray, but that's only because the light source, which happens to be shining right on the box, is located right above the box. If I jump, you'll notice that the top face of the box is gray. But due to the shading model that we're using, no light is hitting the sides of the box, so we don't get to see the actual gray color of the box on the sides. We do see it on the top where the light is shining on top of it. So again, we can fix this just by shifting the box's location. And the way we would do this is we need to change the transformation node value for that box. If we go back into VRealm, we want a scene that sort of looks like this. And to move the box, we can just take the translation value, and if we change the Z component of the translation value, you'll notice I'm moving the box in and out of the screen. So let's go back into C++ here and find the transformation that associates with the box. So here we created the transform, and then we've created the geometry and then the shape node. So this transformation controls that box. Inside here, we can go like this. P node, transform, and we want to change the value for translate, and we want to change it to vector 3. Let's say 0, 0, and let's move it, I don't know, -3 units in the Z direction. Let's compile that, and now run it. Okay, now we see the box is actually located 3 units in front of us. And now the front face, which is facing the light source, is visible, and the back faces, which are pointing away from the light source, is black again, and the top is shaded a different color because it's getting a different amount of light. And you'll notice that the plane that we're walking on gets darker as we get to the corners, because the light source is shining right above, right at the very center where it's most brightest. And then working your way outward is getting darker and darker, but still remaining gray because of the material default color that we've given the box. Now, one last quick thing I'd like to show you, and that is how would we go about to rotate this box dynamically? We're going to go into a couple more VMKs after this one, working around in the scene graph. We'll then go and add some textures and add the material node to it, because we haven't touched on that stuff yet. And then I'll show you some interesting things we can do with transparencies. But in this VMK, I just want to wrap it up because it is running a little bit long. So I just want to show you one other thing. Remember, our container for all of our transformation nodes, or actually all of our nodes, is contained inside of this guy right here. So MVP nodes contains all of our nodes, and the order that the nodes are structured in is represented by these node IDs. And remember, the order that we put the nodes into our container determines the ID number. So the first node that we put inside the container is going to be index 0. So if we want to access it, we can just use this guy here and reference 0 to it, and we'll automatically get this node transform returned to us. And this is helpful because we can do very interesting things dynamically. Let me show you how to do this. I'm going to go and take this chunk of code, and inside update, before I render everything, I'm going to go and modify a couple things. I'm going to create a pointer to a node transform, and I'm going to define this pointer to be equal to the following. Let me just double check MVP nodes. Okay. This is going to return to us the very first item that's stored inside of our container. And we know because of the initialization that it's going to return to us the node transform that controls the box. Having this, we can then do the following. We want to rotate, change the angle, and I'll make it, actually, let me rewrite this. There's an easier way to do this. We're going to get a node transform pointer from our container here. So we're taking the very first node transform, and we're going to change its rotation angle. So every time through this update, we're going to take whatever values inside the rotation angle and just add 0.05 to it. So the first time through it's 0, then it's going to be 0.05, then 1, and 1.5, and so on. So this should effectively rotate our box. And let's take a look. And it does. And now notice which axis it's rotating about. It's rotating about the Z-axis because by default, we've set the rotation angle to be about the z-axis. We can again go back into our initialize, and in here define a different rotation axis. So, oh, sorry, that's the light down here. Node transform. We want to change the axis, rotation axis. And let's say we want to spin it like a top. So we'll do this. It's going to rotate now, but the y-axis, the vertical axis. All right. And it is, but notice that it's actually centered about not itself, but rather some other axis. The result of this is because of the way that the scene graph hierarchy is structured. Let me just take a look here. We create this node, and we have this translation, so this translation is also affecting this rotation. If I remove this completely, then we'll be able to see the box rotating right on its own axis. Okay, and there it is there. Okay, so go ahead, now that you know how to render the plane in the box, you should be able to go and play around in the scene graph, get a little bit more familiar with how things are nested and how things are structured, and then in the next VMK, I'll go through a little bit more detail in terms of what we can render on the screen, how we can manipulate things to get a little bit more comfortable, and then we'll start adding detail into here. We'll start adding textures, we'll start adding materials, we'll start adding transparencies, and all of this will actually become very easy to do. However, you'll notice that there's a lot of code that needs to be written to get this done. This can be a problem, but we'll also fix this by, in a future VMK, we're going to create a parser. Because I'm actually getting very tired of having to recompile anytime we make one little change. Like for instance, if I wanted to change this rotation axis, I have to go in here, change the value, recompile, and then run it. There's actually a much easier way to handle this so that we don't have to recompile every time we change one parameter. And so we're going to go and create a parser for this so we can parse a file that has all the information we need. It's then going to render it through our game engine, and then everything will be fine and dandy. If we want to change something, we just go into this parser file, change one parameter, rerun our program. We don't have to recompile it, we just rerun it, and everything will work perfectly. So that's where we're heading, and I'm sure you guys are going to have a lot of questions based on this VMK. It's a little bit rough on the edges, but please feel free to send messages over to the forum here, inside the community forum. Under game development, when you log in, you'll notice that there's a section for every VMK that I've released. Just post your questions, and hopefully other people that are also working through, they can help you out. When I'm available, I'll be very happy to post my comments in there. And also, if you find any bugs, oh, speaking of bugs, I did find one, which I should mention. This is just a quick one. Underneath lights enabled and lights disabled. If you go under here, you'll notice that we're inside of a for loop going through every single light source. And if the light source is on, we render it, and then we increment this counter. Well, the problem with this code is that if nothing is turned on, this counter never increments. So we need to update the counter even if the light sources are not turned on. So to do that, we'll just take this code, paste it down here, and get rid of the ++ down inside the function call. Same thing has to happen inside lights disabled. Just at the bottom here, update the counter, and then remove the increment here. Okay, so you've got a little bit of scene graph stuff, you have some bug fixes, you have finally rendering on the screen. Go play with it, and send me email messages whenever you have any problems. Send some posts to the community forum, and let's see what you guys can put together now.